This is a Chem Study film, a production of the Chemical Education Material Study. This is the chemical element potassium. Potassium cuts easily. Observe that the shiny surface dulls as it reacts with air. Potassium also reacts with water. By contrast, the element phosphorus is stored in water, but it too reacts rapidly with air. Phosphorus and potassium are similar in reacting with air, but they differ in appearance and in their behavior toward water. Here are most of the 100 other elements. They might also be expected to have similarities and differences. How can we correlate our knowledge of so many different elements? What can we do to order and organize the elements and perhaps even to understand their properties? Well, we can make observations and then seek similarities and regularities. You can see similarities among these elements. For example, many of them are shiny. A few are not. Shininess indicates that these elements are metals. Many metals, such as silver, can be bent without breaking, or like potassium, cut smoothly. Metals are generally ductile. For contrast, sulfur lacks the shine we associate with metals. It is not ductile. Such elements are called nonmetals. Shiny nickel looks metallic. Let's sort the metals from the nonmetals, first using shininess as a criterion. We find metallic copper, chromium, zinc, samarium. In addition to being shiny, metals are good conductors. When we touch these probes, the meter shows high conductivity. When touched to silver, we see that silver is also a good conductor. Let's check potassium. It is ductile and shiny. It is also a good conductor. Silver and potassium are metals. Phosphorus looks nonmetallic. It caught fire in air, hence must be tested under water. Water does not conduct. Neither does the phosphorus. Sulfur looks nonmetallic. And does not conduct. It and phosphorus are non-metals. Lithium is somewhat ductile and looks metallic. The clean surface, like that of potassium, reacts with air. The lithium turns black except where covered with oil. The shininess and ductility of lithium indicate that it is a metal and should conduct. It does. We proceed with the task of sorting elements into metals and nonmetals. Some conduct, and some do not. We come to carbon in the form called graphite. It is not very shiny, and it breaks rather than bends under stress. Carbon is hardly metallic in these properties, but look, it is an excellent conductor. It conducts like a metal, but is not very shiny or ductile. When the testing is completed, there are about 4 times as many metals as nonmetals. Using the criteria of shininess, ductility, and electrical conductivity, we find that carbon and silicon are doubtful. Some 16 elements are nonmetallic. Let's study this smaller group first. We sort out the elements which are gases at room temperature. The atomic numbers shown in red indicate the number of electrons held by the individual neutral atoms. The gases are argon, chlorine, fluorine, helium, hydrogen, krypton, neon, nitrogen, oxygen, and xenon. Of the remaining nonmetals, we sort out the solids. Bromine is the only nonmetal which is liquid at room temperature. We have subdivided the nonmetals into gases, liquids, and solids. Perhaps these gases can be further classified on the basis of their chemical reactions. Potassium, we observed earlier, reacted with air. Since air contains several gaseous elements, let's see which of the gaseous elements will react with potassium. This high vacuum apparatus will allow us to observe reactions between our selected gases and various solids. This mercury diffusion pump sweeps virtually all unwanted gases from the glass apparatus, and this mechanical pump then expels the gases from the system. The pressure in the system is less than 1 micron, that is, less than 1/1,000,000th of an atmosphere. We will use this system of glass bulbs and stopcocks for controlling the flow of the gases we wish to test. Each of these bulbs has been filled with one of the gaseous elements: argon, chlorine, fluorine, helium, hydrogen, krypton, neon, nitrogen, oxygen, and xenon. When this stopcock is opened, the gas can leave the bulb, and if this stopcock were opened, be evacuated through the pump. With it closed and this one opened, the gas enters the reaction tube. A small piece of potassium metal has been placed in each evacuated reaction tube. Starting with gaseous argon, we open this first stopcock and allow the argon to enter the reaction tube containing the potassium. There is no apparent reaction. Let's try heating. The potassium melts. The thin crust of oxide cracks, exposing shiny potassium, which slowly vaporizes, carrying oxide dust with it. The quiet, shiny surface indicates there is no reaction between the gaseous argon and the liquid potassium. Next, we try chlorine and potassium. There is no apparent reaction, perhaps again due to a thin coating of oxide. When heating exposes fresh metal, reaction does begin. Let's try fluorine next. Again, after slight heating, reaction occurs. When surrounded by gaseous helium, the potassium melts quietly. Oxide dust escapes, but there is no evidence of reaction. Apparently, helium is inert toward potassium. When we try hydrogen gas, there is little evidence of reaction at first. But gradually, reaction occurs and considerable white product collects on the sides of the tube. Krypton is next. There is no evidence of reaction with the molten potassium. Here we have neon. Again, oxide dust, but neon does not react. Our next gas is nitrogen. Nitrogen does not react. Oxygen is our next gas. It didn't take much heating to start that reaction. Oxygen is certainly reactive. And now the last one, xenon. Xenon is inert with potassium. Comparing all of the tubes, we find 4 of the gases gave white products with potassium. Apparently the other 6 gases are inert toward molten potassium. You will remember something in air also reacted with freshly cut lithium. Let's try the previously inert gases with lithium. Nitrogen, you will remember, was inert toward potassium. But nitrogen reacts with lithium, as this slow darkening shows. Nitrogen is not inert. Argon does not react, not even with molten lithium. Helium, krypton, neon, and xenon give identical results with lithium. We might tentatively classify these 5 inert gases as a family of chemical elements. Air reacted with phosphorus too. Let's try phosphorus with these 5 apparently inert gaseous elements. Pieces of phosphorus have been placed in the tubes and we're ready to try the reactions. Fluorine will be tried first just for comparison. As soon as it strikes the solid phosphorus, reaction begins. Fluorine is not inert. We now let the inert gases into the 5 reaction tubes containing the phosphorus. The phosphorus is heated until it actually boils. What you see is not a chemical reaction, it is condensing phosphorus. Again, the 5 gases, argon, helium, krypton, neon, and xenon, are inert. Let's group them together as a family of elements. Experiment shows that the atomic numbers of these inert gases are 54, 36, 18, 10, and 2. This is the number of electrons surrounding the nucleus of each inert atom. Now, highly reactive fluorine has 1 less electron per atom than the inert gas neon. Are there chemical similarities among fluorine and the other elements with 1 less electron per atom than an inert gas? Are hydrogen, fluorine, chlorine, bromine, and iodine a family? Let's test this idea. Since fluorine reacted readily with phosphorus, we can determine whether these other nonmetals do the same. Clean pieces of phosphorus have again been placed in the reaction tubes, and all gas is pumped out. When we add gaseous hydrogen, no reaction occurs. Upon heating, the phosphorus boils and condenses, but there is no reaction. When we add chlorine to phosphorus, there is a reaction. Here is bromine. It also reacts with phosphorus. The reaction speeds up when we heat the tube. Iodine is not a gas at room temperature, so we place the solid in the outside tube, with phosphorus in the inside tube. Upon warming, the iodine vaporizes. When the iodine vapor enters the inside tube, we note a reaction begins. Further heating causes a more vigorous reaction, leading after a few moments to this red and orange product. The phosphorus reacted with all but the hydrogen. You'll recall that hydrogen was also different from fluorine and chlorine in its reaction with potassium. Let's find out how bromine and iodine react with potassium. First, we let in bromine gas. Once the heating breaks off the crust on the potassium, a reaction starts. A white product forms. Again, since both iodine and potassium are solid, we have placed potassium in an inner tube and iodine in the outer tube. Heating gives gaseous iodine. In a few moments, iodine enters the inner tube and reacts with the potassium, producing a white product. We remove some of this and each of the other 4 products, place them on a glass plate, and check their reactivity with water. The chlorine compound dissolves quietly. So does the fluorine compound. The bromine compound acts similarly, as does the iodine. When water is placed on the hydrogen compound, however, it gives a rapid evolution of gas. Again, all but the hydrogen compound are similar. Thus, hydrogen is not usually included in this family of reactive and chemically similar nonmetals, each with one less electron than an inert gas. The family of elements consists of fluorine, atomic number 9, chlorine, atomic number 17, bromine, atomic number 35, and iodine, atomic number 53. We have already done a good many reactions with potassium. Perhaps there are other elements of similar chemistry. Let's consider the elements which have one more electron than an inert gas. They are lithium, sodium, potassium, rubidium, and cesium. Let's study their reactions, for example, with chlorine. The gas bulbs are now filled with chlorine and pieces of the 5 metals placed in the reaction tubes below. We add chlorine, then heat the lithium. There is a reaction with the chlorine, producing a white product. Sodium melts. The crust cracks, and the liquid sodium reacts vigorously, again producing a white product. Here are potassium and chlorine. Again, a white reaction product collects on the walls of the tube. Next, we try rubidium. A white solid again results. Finally, cesium melts quickly, then reacts, also producing a white solid. As with the inert gases and the reactive nonmetals, these metallic elements also show marked similarities. Perhaps they too are a chemical family. All these elements are stored in oil since they react with air and water. Let's check their reactions with water. Here's lithium. Next is sodium. Potassium reacts with such vigor that the gas produced bursts into flame. Rubidium is similar. Cesium reacts almost instantaneously. Their similar properties show that we have isolated a third family of chemical elements. This simple table could be expanded by further experiment to become the periodic table. Each column contains a family of elements. The number of electrons per neutral atom increases regularly in each row. We have seen that each of the elements is different from all the others. Starting with samples of most of the chemical elements, we studied the reactivity of all the gases. 5 gases reacted with none of the other elements. They constitute the inert gas family of chemical elements. Atoms with the number of electrons represented by these atomic numbers are especially stable. We then studied the nonmetals having one less electron per atom. These elements all had similar reactions and formed a second chemical family. Finally, we discovered a third chemical family. Each atom of these elements has one more electron than an inert gas. Thus, the inert gases were our key to discovering families of elements, and the atomic numbers were our key to arranging the families in the periodic table. But research continues. Some of the gases previously thought to be inert have been made to combine with reactive elements. Xenon and fluorine were being passed through equipment such as this, even as the preceding film was being completed. The gases mix, then pass through a nickel tube heated to 400 degrees centigrade. The product collects in this cold trap. A white compound is formed. It is xenon tetrafluoride. The xenon tetrafluoride reacts vigorously with water, producing an unstable yellow intermediate which decomposes to give an aqueous solution of colorless xenon trioxide. Similar krypton compounds have also been discovered. The similarities of these compounds further strengthen our belief in the concepts of families of elements.